Okay, good morning, everyone. You are now working on your final project. Just a reminder, please make sure to read over all the instructions about expectations for final project. And therein, you will find that your first milestone is due, as usual, 11:59 p.m. on Tuesday. You're spending between now and then thinking up exactly what you want to do, how exactly you want to break it down into 4 digestible pieces, and then how you're going to show us rather than tell us that you've implemented each of those 4 pieces. Screenshots and video. We can't look at your code and tell whether you've implemented your milestone or not. Any questions about the final project milestones? All good? Okay. All right. So back to lecture material. We finished last time talking about collective robotics, otherwise known as swarm robotics, trying to design swarms of robots to do something that would be beyond the ability of any one machine, which is a good way to go, but it's got its own problems, one of which is how do you get the group as a whole to coordinate? And we looked at an experiment last time that looked at 9 different slightly different evolutionary algorithms that tried to evolve groups to work together in different ways, and we saw the benefits and drawbacks of those different approaches. Actually, that's a good reminder about your A/B testing, which you're going to be conducting in 4 weeks' time, which is you're looking for slightly different versions of your idea that facilitate or obstruct the evolutionary algorithm's ability to evolve whatever it is you want your robots to do. Are you making things harder or easier on the optimizer? Yeah? Okay. We ended last time by saying coordination is great, but if you really want to coordinate at scale or for complex or challenging problems, you're probably going to need communication. So we're going to look at another classic paper in the field today in lecture 19 that looks at machines that are evolved to communicate. And interestingly, we're going to see, we wouldn't be talking about it if they didn't. They do evolve the ability to communicate. What do they say to one another, and how exactly do they say it? That's what we're going to be looking at today. I mentioned this is a classic in the field. We're going to go all the way back to 1991, to the very beginning of evolutionary robotics. So we saw back at the beginning there were sort of 2 papers published at about the same time on this idea. This was published about the same time and is arguably kind of the third starting seed for evolutionary robotics. Again, we're not dealing with complex physics engines here. We've got a very simple toroidal grid like we saw last time. However, in this case, our toroidal is not continuous, it's discrete. It's made up of a bunch of discrete cells, 200 by 200 of them. And again, think about this rectangle that you're going to see here, folded so that the 2 long edges touch, and then the 2 ends of the cylinder touch. So we have a toroid with a whole bunch of grids on it. And this is the only lecture we're going to see where the robots running around in this world are gendered. We've got 800 females and 800 males. Why? The reason why is the authors who wrote this paper were biologists, and they were interested in not just the evolution of communication, but sexual evolution. So what is it that males do that attract females to want to produce offspring with them, and vice versa? So these 2 sort of questions are intertwined in the experiment we're looking at today. This is not a course on evolution, so we're not going to talk about sexual evolution too much. We're going to focus instead on the other part of this experiment, which is the evolution of communication. Okay. As you've probably already noticed on this slide, there's some interesting and seemingly arbitrary experimental design choices that are already being made. Like a usual evolutionary algorithm, they're going to start by dropping 800 females with random controllers into this toroidal grid. They're going to drop 800 males with random controllers into this grid. All 1,600 robots or agents, all 1,600 agents are able to sense, think, and act, but they have different sensors and different actuators. They are able to sense and think and act in different ways. Females cannot hear. They cannot move. They stay where they are, but they can signal. They can emit a signal. Males are blind. They cannot see, but they can hear. They cannot signal, but they're mobile. Again, seems kind of odd. There are cases in nature of male and female versions of the species that are better at worse at different sensor and motor capabilities. Okay. Let's have a look inside the brains of these 800 male agents and 800 female agents. Again, this is an old paper. I apologize for the quality of the figures here. This is the female's controller up here in the top. It is a neural network. Inside any one female, there is a set of sensory neurons, hidden neurons, and motor neurons. Same thing for the males. Inside every male is a neural network controller that has sensor neurons, hidden neurons, and motor neurons. Let's start with the females. So the females can see, but they can't hear. So their sensor neurons are visual sensor neurons. Might be hard to read here. It says here, male detected to the southeast, and the male is facing to the east. So what you're going to see in a moment is the males moving around, represented by the arrows here, and the females have a sensing radius. Remember the boids, they can't see an infinite distance, but the females can see up to 2 cells away from themselves. If a male ever moves into their sensing radius, where they can sense, they know where that male is relative to themselves. What kind of sensing is that? We talked about that last class. This female sees that there is a male to the southwest of her, moving to the west. This female sees that there is a male to the southeast of her, moving south. Deictic sensing. So the females are seeing males relative to themselves, and they also are sensing what direction the males are heading in. So you'll notice that the sensor neurons here have zeros and ones inside. The sensor neurons are binary values. The females have 8 sensory neurons. 4 of them indicate the direction in which they see a male. If there is no male in their environment, all 4 of those sensor neurons are 0. If there's a male to the south, northwest, it lights up. If there's the first neuron lights up. If there's a male to the northeast, the second neuron lights up, and so on. The other 4 sensor neurons represent the direction of travel of the male. So first sensor neuron indicates whether or not the male is heading north, south, west, or east. Again, kind of arbitrary decisions. They're making a very, very simplified agent that's able to see. If a female has more than one male in her sensing radius, what arrives at her sensor neurons is information about the closer male. So she can only see one male at a time. So far, so good? Okay. Everything else about the neural network, relatively familiar. Values flow from sensor neurons to hidden neurons. You'll notice that there's some recurrent and self connections here, which tells us that the females, at least in principle, are capable of memory. They can remember where males were and in what direction they headed in the past, if that tends to be useful for what we want them to do, which we haven't seen yet. The values that then arrive at the output layer, they are also binarized, 1, 0, 1, 0, 1, 0. Let's assume for the purposes now that there are also 8 motor neurons here. These motor neurons become pressure waves in the larynx, which causes the female to emit a song. What's the song? In this cartoon example here, the song is 101. Not the most beautiful song you've ever heard, but there it is. Okay, why is it called a song? It's called a song because when she emits that set of binary values, If there are any other males in her singing radius, which is the same as her visual radius, those males, quote unquote, hear the song. You can guess hopefully where this is going now. The input layer for the males is their auditory neurons. They receive, we just copy the binary values that are emitted by the female into the input layer of a male's controller if that male is inside her singing radius. So far, so good? Okay. As you can see, the cognitive architecture, the way in which the neurons and synapses are wired up, is identical inside the males as it is in the females. The males have an output layer as well, but now you can see that the output layer has not been binarized, but it has been discretized to integer values. There are, in the experiments we're going to see, there are 4 output neurons. They should have just drawn the 4th one here. There are 4 output neurons, which represent the 4 motor primitives that the male can perform. One of 4 simple actions. If the first output neuron has greater magnitude than the other 3 motor neurons, that male stays still, stays where it is. If the second neuron has higher magnitude than the other 3 neurons, the male moves forward. If the third neuron has the highest value among the 4 neurons, it turns left. And if the 4th and final neuron has the highest magnitude, the male will turn right at that time step in the simulation. Where have we heard about motor primitives before? I'm going to press on your short-term memory today. We saw a robot that was capable of motor primitives, very simple, short-lived in time actions that was then taught to stitch or compose them together into more complex actions. Not quite BabyBot. BabyBot learned self, non-self discrimination and how to play with fruit put in front of it. You remember the little cute robot that would shake the block 3 times left and right, up and down, forward, back? That robot was taught motor primitives and then was taught how to compose those together. Okay, no composition here, just males that are capable of a few simple actions. All right, we're back in 1991. This is a very simple experiment, at least simple experimental design, but we wouldn't be talking about it if something interesting didn't happen. Okay, all right, so just to recap, female network input takes position and orientation of the closest male in her visual range. The output of the female is her quote-unquote mating call. All right, another hint about what's going to happen in this experiment. Male, the mating call is received at the input layer if that male is within any female's range, otherwise 0 vector. So if the male is moving around and there are no females nearby, the male hears nothing. Zeros enter the input layer, and here's the 4 motor primitives. So far, so good? Okay. Okay, all right, things start to get a little more interesting now. If a male finds a female, so if a male moves around and ever moves into the same cell as a female, a reproductive event occurs. We take that male and that female, we make a modified copy of each of them. We copy their neural controllers and slightly change the synaptic weights randomly inside those 2 new copied controllers. We take that new son and daughter. Remember, we have gendered agents now. So we have 1 male offspring and 1 female offspring from this event. We find some other poor hapless male in the environment and some other poor hapless female in the environment, delete them, and put the son and the daughter in those recently vacated place. This is arguably the oddest evolutionary algorithm you're going to see in this class. What just happened? What parts of the evolutionary algorithm did we just see occur?
Sexual reproduction.
There's selection going on here, or there might be selection going on here, which is
whoever isn't having sex they're out.
they're out. There you go. That's about as a succinct description of this experiment as I've heard. That's it. Where's the fitness function? This is arguably the most realistic evolutionary algorithm you're also going to see in this class. There is no fitness function.
I was going to say it's pretty much like your ability to find a partner.
So there is selection, as you can imagine, there is selection pressure that is going to start operating in this environment. And that selection pressure is going to favor males and females that can get together. That is the fitness function. There is no explicit equation that's determining who lives and who dies. It's just a byproduct of the behavior. How the females see and sing, and how the males hear and move.
So is this like they don't run multiple simulations for every generation, just one simulation gives multiple generations?
You got it, right? There are also no explicit generations here. They're just going to run the simulation forever. Let's see what happens.
I guess just looking at this diagram, this might just be a diagram, but like the selection of that male, I know there's
Which one?
the male close to the female. Is there a way they're
This one?
Yeah. Is there a way they're actually picking the male? Because I mean, with the amount of things out there, it could be almost kind of arbitrary as to which one gets just.
It is arbitrary, right? So at this moment in time, at this time step of the simulation, this male and female are cohabiting the same cell. And so the other 799 males and the other 799 females are equally likely to be deleted. Okay. Okay, off we go. I love this experiment. No cool graphics. We're going to do everything with tables, but trust me, there's some cool things we're going to see happening. Okay. They ran different versions of this experiment. The first one is they're going to restrict the females to 8 different songs. So think about the controller for the females. They're going to restrict the output layer to 3 motor neurons. Remember, the motor neurons for the female are binary. So any given female with a random controller or otherwise can emit at any given moment in time one of 8 songs. These are the 8 songs. What does that mean about the controller of the males? What do we need to change about the cognitive architecture of the males?
They need to have only 3 sensor neurons.
They're going to have 3 sensor neurons, right? So we're kind of restricting that waste there. We're going to narrow the output layer of the females and narrow the input layer of the males. Drop all 1,600 agents at random places on the toroidal grid. Set every one of their controllers to have random synaptic weights, and turn on the simulation. At every time step, each of the 800 females listens and emits one of these 8 songs. Then each male, if they hear or not, they perform their motor primitive, go to the next time step, and repeat. Okay, so at the end of 100 time steps, they found that across all the 800 males, for all of those 800 males at this 100th time step, whenever any of them heard song 000, 25% of them would move forward. 38% of them, when they heard this song, would turn right. 9 of them, when they heard this song, would turn left. 28% of them, whenever they heard this song around this time in the simulation, would stand still. Here's the percentage of what the males did whenever they heard song 001. What's happening?
They're learning to communicate.
Are they learning to communicate yet? These are percentages marching across each row that sum to 100%.
This doesn't seem that much better than just random chance.
Doesn't seem that much better than random chance. Is it better at all? If there's any statisticians in the room, if you look at these numbers, they don't look that different from 25, 25, 25, 25 marching across any row, which is what you would expect for random males and random females. Remember, it's a little noisy, right? So it's hard to say, but at this point, if you're a good scientist and you're skeptical, you'd probably, if you were forced to guess, nothing's happening. The males are quote unquote ignoring the females, or at least they're not reliably doing anything in response to a song, and the females don't seem to be doing anything either. Everybody see that?
Be interesting to see if you, without like modifying offspring, you ran this for a little bit to just see how many males are actually making it to females based off of where their evolution is at.
Good point, yeah. So what's not reported here is the frequency of reproductive events. What would you think? How often are folks getting together at this point? Not that great. People are moving at random, and among the males, they're only moving forward a quarter of the time on average. Turn left and turn right. Sorry, I should have said this before. Turn left means turn left inside the cell. Turn left on the spot or turn right on the spot. You're not leaving the cell. Remember, the 800 females aren't moving either. It's pretty low that there are reproductive events going on. Any other observations before we move on? But there must be some reproductive events occurring. So we've now jumped forward in time, same simulation. Now we're at time step 5,000. And the table is again reporting on average, what do males do? Now, on average, when males hear song 0, 0, 0, 0, 74% of the time they move forward, and much fewer of the times do they do anything else. What's happening? Clearly, things are no longer random, right? We are clearly very far from 25%, 25%, 25%, 25% in any given row.
I mean, I obviously don't know their behavior, but they're no longer standing still, which is good. It looks like they're mostly moving forward. They're probably figuring out the general heading and then heading that way. They're turning less.
So first observation, the males at least are much less of the time staying still. If you're a male and you want to reproduce, the worst thing you can do is just stay where you are, because you know by definition in that cell there are no females. Okay. My apologies for the male-female jokes, but typical males here, right? They are ignoring the females. Look at the column. Just in general, they tend to move forward regardless of what the females are saying. Is there no evolution of communication yet? There's definitely evolution occurring, evolution of behavior, but not communication. We're 5,000 time steps in. We're quite a ways into the simulation. Why not? We're getting evolution of behavior first, but not evolution of listening or evolution of communication.
Just kind of scaffolding. I think you have to learn to move before you can learn to move somewhere specific.
Possibly. Remember at the end of last class, we were talking about evolution of communication is hard. Both the sender and the receiver have to reliably send and reliably receive the signal and act appropriately in accordance with that signal. Do you think the frequency of reproductive events at this moment in time is higher or lower or the same as the frequency of reproductive events way back here near the beginning?
I feel like there's way more just because there's way more movement happening in general.
Sure, right? The males are covering more ground, and just by chance there's going to be more reproductive events. And the sons of those males are going to tend to also move in a straight line. 7,500 time steps into the simulation. Now we've got real typical males. I don't know about the investigators of this experiment, but I imagine at this point they were probably kind of nervous, right? They certainly got evolution of behavior, no communication. We wouldn't be talking about this lecture if this was the end. 15,000 time steps later. Now what's happening?
This feels like they're starting to evolve communication because you're getting on the turn left and turn right large percentages on it. So it's becoming like a specific song to tell it to turn left or to tell it to turn right.
It's becoming, it being this song, is becoming the song that means turn right. So now we're going to start talking about songs that mean things. We've suddenly moved from a very simple experiment with gendered agents, with very, very simple neural network controllers inside, to almost the philosophy of meaning here, right? We're almost switching now into a linguistics course. What does language or words or songs in this case mean? But we're going to avoid drifting into philosophy because here meaning is very concrete. Meaning has been operationalized, meaning when we talk about the word meaning, what we mean is it means this. It causes this kind of behavior in receivers. Does this song mean left to everybody? Or sorry, all the males? I see you shaking your head no. Why not? How do we know it doesn't necessarily mean that to all the males?
There's 22% that still just go forward.
Okay, so there's still a minority of males in the population at this time that don't, quote unquote, understand what 101, quote unquote, means. They don't do the right thing when they hear that song. What is the right thing? The right thing is what the majority of males do, and why is that the right thing to do? This song could mean turn right, but it's not the right thing to do.
It's just the agreed upon meaning.
Sorry?
It's the agreed upon meaning.
How? We want to avoid philosophy this morning, right?
It's what got the 77% to reproduce.
That's it, right? It means turn right, and if you understand that that's what it means, and you obey that command, it's good for you, and for your offspring, and for their offspring, and so on. So there is an evolutionary advantage. There's a selection pressure on the males to do the right thing when they hear this particular song. All right, what about song 110? It clearly has meaning. For some, for all. Almost all the males at this point, right? It's more entrenched. Yeah? Okay. What about these other 6 songs? Do they mean move forward? Looks like it. Whenever these males hear this song, that's what they do. Do these songs mean go forward? Not really, right? Remember, they weren't listening before. They would all just do this by the males, or at least the male ancestors of these males didn't listen. They would just had a default behavior. So in answering this question, what do these other 6 songs mean? The only way to really answer that question is to go back and look at what the ancestral males were doing. What do these songs mean to the females, if anything?
Could it be that there's no males within their sensing radius?
Possibly. That might be answering the question of what do the songs, when do they emit this song or that song? Yeah, definitely. We're going to see they definitely change their song, or there are certain females that evolve the ability to change their song when males enter their visual range. But what did the songs mean to the females, if anything? If we were to ask the females that emit this song what it means to them, what would they say, hypothetically?
Assume it's, to them it means something related to the location and direction of males within their range. They can see this song is more likely to end in me reproducing.
What this song means is it's more likely for me to be able to produce sons and daughters than if I emit the other songs. I'm deaf. I can't even hear the song. I may not know, quote unquote, that I'm emitting it, but that's it, right? That's the reason, quote unquote, the reason why the females emit it, because evolutionarily it increases their chances of reproduction. So far, so good? Okay. All right, this is, again, apologies for the figure quality here. They're going to show a cartoon of how this works. So in these experiments so far, here's what we've seen. Way back at the beginning, males wandered randomly, females signaled at random. Not surprisingly, males that stood still went extinct. Those that didn't, the ones that survived, were the ones that stood still for less time, and by evolution amplified the signal until eventually males evolved to move in straight lines. But they ignored signals. There had been no mutation events that had led to a sender and receiver simultaneously, quote unquote, agreeing on the meaning of a song. We just saw that males evolved to turn in the presence of certain songs. And actually, these males are taking a risk when they turn in response to a song. A risk how?
They can't move forward, so they're standing still.
They're standing still. They're burning one time step when they're guaranteed not to reproduce.
Female also only sees one male at a time. That could have been a song meant for someone else.
That could have been a song meant for someone else. Things are going to get even more interesting in a moment. Okay, hold on to that thought. Okay, so what was happening at exactly this moment in evolutionary time we just saw? What was happening is that we saw that males tended to turn in the presence of two of the eight songs. More specifically, males had evolved to turn when on the same row or column as a female. So here's our female in the middle of her song range. It turns out that she will emit song 6 and 7. She will tend to emit songs 6 and 7 whenever a male arrives within her sensing range in the same column as her or the same row as her. So somebody mentioned this a moment ago. She will sing a certain song, which may or may not mean go forward, but the males tend to go forward. And if they have entered her visual, range, that males on average tend to do what they usually do, which is go straight. They're going to hit one of these rows or columns, and at the moment they do, most of the 800 females will then switch to either song 6 or 7. So females have evolved to signal this information. So we said, what does the song mean? It means turn left or turn right. We could also probably reliably conclude that those songs mean you're close to me, and you're on either the same row or column as me. You remember the warmer, colder game? It's kind of like that. Okay. Females that don't have the ability to use this signal, they don't have the right set of synaptic weights to exhibit this behavior. They enjoy less reproductive events and eventually go extinct. As this experiment continues to go forward, the females evolve to use this signal in more situations. So the situation I just described, that might happen for this cell, and this cell, maybe this cell, maybe this cell. Later in time, the females are doing the same thing, but for all of the shaded cells here. No matter where males arrive on the female's row or column, they sing the right thing. Okay. We're going to just take a pause from this question.
I was just say it's interesting looking at
probably going to be reproducing less if they're only doing one thing heading in a straight line. Some may, but now the ones that reproduce, that reproduction is going to matter more. And there's probably less reproduction, so that's going to lead to more reproduction, the actual evolving of like a meaning to a song.
Absolutely. That's why at this point we have this situation. For these males that turn, evolve the ability to turn when they arrive at the same row and column as a female, assuming the female is emitting the right song. If they both do the right thing at the right time under the right circumstances, those pairs are going to reproduce more often than pairs in which the males just move forward. That's why we now have this situation. Yep. Okay. All right, we're going to pause for a moment. We're going to look at an interesting kind of like, this is almost like a sanity check that they ran. They were kind of debugging their idea about what's going on in this experiment. So we talked about controls, I think, last time, the A/B testing. Think of A as like the control. So they did a control set of runs in which males were deafened. So they ran back the evolutionary tape to the beginning, dropped 1,600 random males and females. Everything was the same except the males couldn't hear. That was the only difference. Which one is that? That's the control here. Again, apologize for the quality of this figure. It's this curve here. This is the control curve. And this curve is the test. This is the experiment we were just looking at. Okay. We have evolutionary time on the horizontal axis. And just to remind you, we're not looking at evolutionary time, which is made up of a sequence of a large number of simulations. We're looking at just one long simulation running. On the vertical axis, they're reporting the average number of moves a male made before finding a female. You'll notice, obviously, both curves start to drop, which is evidence that evolution of behavior is occurring in both populations, the control population and the test population. The evolution of reproduction or acceleration of reproduction is occurring. That's sexual evolution at work. Yeah? Okay. Not surprisingly, in the test experiment, which is down here, later in evolutionary time, there are a lot of reproductive events going on, more than in the control case. So male in the situation in the world or the simulation in which males can hear, more reproduction evolves to occur than compared to the control, which is where the males are deafened. So we know that in the control case, no evolution of communication can occur. The males are deaf. Okay, so that all kind of makes sense. But let's focus in this region here. In this early part, in the first 5,000 time steps of the simulation, both lines are dropping precipitously. So there's definitely evolution of behavior occurring during these 5,000 time steps. And counterintuitively, the control males and females are evolving to reproduce faster than the test males and females. Why? It may seem counterintuitive on the surface, but if you think about it, it actually makes sense.
Maybe because the control, they're not worried about the song, they're just worried about what behaviors, like standing still, need to go for, get out of there so that the most likely things can occur, whereas the ones that can hear, they're doing that, the song is also factoring and slightly changing how they're moving, and it's going to take a little longer to do that because there's more factors in it.
The deaf males aren't hearing any songs. They're not, quote unquote, distracted by songs. They can, quote unquote, focus on evolving to go straight.
Out of curiosity, what are the inputs for these deaf males?
I think it was just 0, 0, 0, 0. So remember, there's self and recurrent connections, so they can evolve to do, actually they only need to evolve to do one thing, go straight, more or less, right? That if you can't hear anything, that's the best strategy. The reason we're talking about this is the gap between these two lines. This is the cost of the evolution of communication, right? At the beginning, if evolution of communication is even possible, and in this situation it is possible, it's not inevitable, but it's possible, there's some awkwardness. There are males that do the wrong thing, where if only they had done the right thing, there would have been more reproductive events. So it might be that the females actually get a little bit better at changing their song when males arrive on their row or column, but those males are just not getting it. They're not doing the right thing. So those females, they're not attracting males. They've got just as equal a chance of being overwritten or deleted as any other female. And so evolution of communication fails. It's a little bit tricky, right? So there's like stops and starts where maybe the receiver is doing a little bit of the right thing a few times, but the sender is not, or vice versa. There have to be a series of mutations that allow enough of the receivers to do the right thing and enough of the senders to do the right thing for reproduction events to become common enough that we start to get an increase in the numbers of reliable senders and reliable receivers, which starts to occur in these pair of experiments, or in the test experiment here, at around, whatever that is, 7,000 time steps. It's possible, but tricky. Okay. This is obviously a very abstract experiment, but there is work underway to get large numbers of drones to evolve or train or discover their own language. We could obviously program into drones, here's how you should sense each other, and here's what you should do when drone I tells you to do this. We as humans could try and come up with a language for large numbers of machines that are trying to coordinate in the real world. There are many in the field that think maybe we should do something like this. Let the machines figure out their own language that is efficient, has reliable senders and receivers, and ultimately allows them to coordinate to do what they want to do as a whole, which in this experiment is just reproduction. So very abstract this morning, but it actually does have real-world implications. It's also scary because if drones or autonomous vehicles are evolving their own language and some of those senders and receivers are not 100% reliable, that's not so great, right? There are some very fast-moving autonomous vehicles on a highway. They're moving at very high velocity and they're very close to one another. The one in front tells the one in back to slow down a little bit, and the receiver misinterprets that signal and instead interprets it as speed up a little bit, right? Not great. Okay.
Did this experiment on a long enough runtime get to a point where like signals were giving 100% for like each specific move that a signal is trying to do?
Okay, so back to this experiment, right? Did evolution clean this up completely? We'll see. Okay, we'll see. Okay, again, apologize for the cartoons here. Let's see this process of reproduction in action. Panel A here, we have the female in the middle, and apologies if it's hard to see. She is currently emitting the song 000. In panel B, the male enters her southwest quadrant. So from her point of view, deictic sensing, she senses a male suddenly present to the southwest, and she can sense that the male is moving north, and she switches her song to 101. She continues singing 101, and this male does what most of the males in this experiment tend to do, go straight. The male arrives on the same row as she does, and the moment she does, she switches to song 011. The male turns right. You can see the little black arrow here is now pointing to the east. And the moment the male turns to the right, the female switches back to singing 101, which at least from the perspective of this figure, seems like song 101 means go straight, which the male does, and we have a reproductive event. Okay. Here's a better example. This is actually, a better evolved female signal. So the females at this moment in time have gotten better at communication. What does that mean? It means they can use more songs and cast a wider net. They can now attract males that are exhibiting a wider range of behaviors. So now we have a male coming in from her northwest. She's singing 110, male goes straight. She switches her song, which the male doesn't seem to care about and continues to move straight. She switches back to 110. The male arrives here and she switches to 101 and the male turns left. Uh-oh, that's not great. However, the female keeps singing 101, which at the previous time step caused the male to turn left. So we know that male is going to continue to turn left. Left, left, left. Left. Now she switches to 011 and the male goes straight. So she can convince males to approach her even if they're to the north of her and they're moving east to the northwest and they should be turning to the right. They don't do what the female, quote unquote, wants the male to do, but the female knows how to handle that situation and has another song in her repertoire to deal with that situation. So now, at least in this anecdotal example we're seeing here, it's anecdotal evidence, but we start to have some evidence that not only is the evolution of communication occurring, but the evolution of increasingly rich or useful or flexible language is starting to evolve. So some of these males, they don't actually know how to turn left or right, so they don't know how to interpret songs. The only thing they can do is go straight and turn left. My great uncle escaped from Poland just at the beginning of the Second World War, got to Canada by the skin of his teeth, and not surprisingly was a very nervous individual. He learned to drive. I grew up in Toronto, big city, even back then. But he never got the hang of like turning left. He didn't like going through an intersection with a lot of busy cars. So anywhere he went in Toronto, which like New York is a big grid of streets, he would always make rights. Never made a left in his whole life, but he got where he needed to go eventually. This agent always reminds me of my great uncle. There you go. Okay, back to the experiment. We're going to look at a different experiment. Same situation. Things are going to get more interesting in this experiment. And I run sort of counterintuitively, this experiment is simpler. They're going to go back to the beginning, drop 1,600 random agents. Now they're going to restrict the output layer of the females to just 2 neurons. And they're going to restrict the input layer of the males to just 2 neurons, which means the females can only emit 1 of 4 songs, and the males can only hear 1 of 4 songs. Why did they do that? It's because they wanted to be able to draw in a table, and we'll talk about this table in a moment. They wanted to be able to draw or report the individual behaviors of every single male in the population, all 800 males. Okay, how did they do it? Okay, the way they did this is, you'll notice that every element of this table is an integer to the left of a colon and 4 digits to the right of the colon. Okay, the figure to the left of the colon reports that number of males. So let me just take this cell here in the upper left. So at this moment in time, the very first time step of this simulation, 6 males, did this, 0001. What does that mean? The 4 digits here correspond to the 4 possible songs. So the first of the 4 digits, this is what the male did when he heard song 1. The second digit is what those 6 males did whenever they heard song 2. This is what the males did when they heard song 3. And this is what those 6 males did when they heard song 4. The number itself can be either 0, 1, 2, or 3, which is stay still, go forward, turn left, or turn right. Okay, so what is this table telling us? In this cell, it's telling us that at this moment in time, there were 6 males that would stay still, 0, whenever they heard the first 3 songs, and they would go forward if they heard the 4th song. This is the very first time step, so these males haven't heard anything yet. They've just arrived on the toroidal grid, but we can obviously pass values through these 800 random male controllers, and we can see what those males are thinking about doing. We can see what values arrive at the motor neurons. Everybody with me so far? Okay, there's a little misprint in the upper left here. This should be 4 colon followed by 4 zeros. What do these 4 males do? They're grouped together because they have the same set of behaviors, which is
They all stay still.
they stay still no matter which of the 4 songs they hear. Let's just practice that we understand how to read this table, because we're going to see several of them in a moment. What do these 4 males do?
Go forward and turn right. Or
And-
stay still, stay still.
Under what conditions? How do we read the 0013? How do we interpret the 0013 here?
Song 1 and 2 means stay still. Song 3 is go forward, and the 4th song is turn right.
Exactly. That's it. Okay. Last one. Let's jump to the bottom right. There are 6 males that do this. What is this? What do they all do?
Leads in a circle, it just turns right.
They turn right no matter what they hear. What do you think the evolutionary future is for those males? Right? So even at this moment in time, you can see this distribution. There is a very rich distribution of male behavior. There is a male somewhere among these 800 that'll do something. Anything you can imagine under the sun, they'll do it. But you can already see some of these males are doomed, and some are destined to produce sons and daughters, grandsons and granddaughters, and so on. Which ones in here look like they have a sunny evolutionary future ahead of them?
Ones that can go forward.
So these actually might do okay. They're not communicators, they're not good listeners, but they're more likely to reproduce than these down here. Okay. So before we start now rolling forward in evolutionary time in this experiment, everybody see how to read this table? Any remaining confusion? Okay. All right, here we go. 8,000 time steps into the future. What's happening? Lots of observations we can make about the males, and if you're paying attention, we can indirectly conclude things about the females as well. Let's start with the males. What's the first thing that jumps out at you? This compared to this.
A lot of those cases where they were just spinning and not doing anything got cut out like immediately.
Yeah. So much less male behavioral diversity. Okay. What else is going on?
The large majority of the action for the first song is a 1, so the females seem to be kind of learning to tell them to go forward.
Absolutely. So already at 8,000 time steps, we have the evolution of communication. Good eye. So if you look at most of the colons here, the first number to the right of the colon is a 1. So song 1, there's 4 possible songs, remember. Song 1 seems to mean, for most everybody, go forward. Doesn't mean go forward to everybody, every single last male. There's a couple of non-1s to the right of a colon. Question or comment?
They seem to either turn left or turn right. They're not, the successful ones aren't doing both.
Yes, my great uncle doesn't exist here, right? They can turn left or turn right.
It's not, they haven't totally done it, but they're slowly evolving out, staying still. There's much fewer zeros.
The males are moving. You want, if you're a male and you want to survive in this world, you'd better keep moving, no matter what. Okay. You can see also that things are starting to clump up, right? So there's a few stragglers out here, but there are several cells in which there's a very large integer to the left of the colon. So I've highlighted one of these clumps here. Out of 800 males, there are 547 of them. The majority of males have this response to females that emitted only songs 1 and 2. So let me just pause for a moment. What can you conclude about the females? What are they doing? What are they singing? Go forward and turn. So as we've already pointed out, most males go forward when they hear song 1. Presumably the females are singing that most of the time. When a male enters their sensing radius, they don't want the male to stop. They probably want the male to continue until the male reaches the same row or column, or maybe they have some other strategy, but they need to keep the males moving once they enter the periphery of their sensing range. So we know that most of the females are emitting song 1. If you're a female and you never emit song 1, that's probably problematic. Same thing for song 2, because song 2 causes this majority of males to turn right. If there are these many males that are all turning right whenever they hear song 2, not song 1, not song 3, there are probably a large number of females that are emitting song 2, and they quote unquote know when to do it.
It seems like the males are just learning that song 2 just means turn, because right above it you've got that 323.
Yep.
And it's the same. And that's, so 800 something of them.
Yeah, interesting, right? So there's two groups of males, these males and these males, that quote unquote interpret song 2 differently. Is that good news or bad news for the females?
It might not matter what direction they turn in, because it might just have them turn until they reach the proper direction, even if it's like 359 degrees.
Exactly. There's opportunity here for the females, right? If they can handle both of these situations, then those females are going to successfully mate not just with these individuals, but with these individuals as well. I'm noticing now that I must have misspoke. There's 547 males here, 323 males here, so there's got to be more than 800 males. Okay, more than 800 males. Doesn't really matter for our purposes. It's the relative numbers that matter. You can probably see now why this paper is a classic in the field. Very, very simple experiment. We're getting very interesting and rich evolutionary dynamics. Anything else we can conclude before we move on?
I found your uncle. He's at the bottom of the column.
The bottom of this column?
Yeah.
There we go. That's right. There's one. Thank you. Excellent. Still around. Okay. Good to know. Other observations? Okay, let's keep going. All right. Same experiment, 2,000 time steps later. We've jumped from time step 8,000 to 10,000. Now what's happening? Well, I guess I'm kind of giving away the punchline over here. So clearly there's still a big clump up here. There's another clump that's emerged up here. This clump up here, these are males that are responding to females that emit only songs 3 and 4, which I'm kind of cheating. You can't see that information in this figure. Although, again, I guess you can indirectly infer it because there's a significant number of these males. So for these males, songs 3 and 4 mean go forward and turn right. Songs 3 and 4 for these males mean something different, slightly different. Yeah? Okay. So it turns out that, although you can't see it from this figure at this point, there's two groups of females. Males are responding to only one of these groups. So the group of females that are good at songs 1 and 2, they're mating with these males, and the females that are good at emitting songs 3 and 4 are mating with these males. This is not the end of the story. We've got a couple more slides to go. What remains possible here? Put yourself in the shoes of a male or a female.
They kind of combine and we get 13, 13 is the majority.
Why? What's so good about 1313? There's 1313 down here.
You would respond to both the females that are on emitting 0, 1, and 4.
Yes, okay. I'm resisting all the jokes about human males and human females here, but we have one group of males up here that's monolingual, speaks one female language. There's another group of males over here that are very good at interpreting another female language made up of 2 songs. These males can't understand these females, and these males cannot understand these females. If you're an enterprising male, you want to evolve the ability to become bilingual. Regardless of whether you by accident stray into the song radius of this set of females or this set of females, you do the right thing. So what do you think is going to happen? We've got a large group, 2 large groups of monolinguists and 1 small group of bilinguists down here. Again, I've kind of given away the punchline, right? Okay, here we go. 10,000 time steps. 12,000 time steps. I just said this. Males 1313 are bilingual. 14,000 time steps. 16,000 time steps. 20,000 time steps. 30,000 time steps. 40,000 time steps. Okay, for those of you that only speak one language, hint, hint.
I was curious as you were going through it, 1, 2, 1, 2, it's also kind of exhibiting the same behavior, and I was expecting it to get down to 2, like 2 majorities, 2 modes, and then combine into 1, 2, 1, 3, or something else.
Great catch. Yeah, there's a lot going on here. So what is going on among these 78 males at 14,000? And then there's there's a few more of them at this time. Are they monolingual, bilingual?
They're bilingual, the ones to the left a bit and 2 above.
Yeah, there's some more. What happened?
Is it that the females are mostly figuring out how them to turn right, and that's not really?
It's probably some detail of the way in which these different groups of males respond to those 4 signals. It's what's probably happened, and I don't think this was reported in the paper, this is my guess, is that these males and the females associated with them were turning, they weren't my great uncle. They only turned once and were heading in the right direction. They didn't have to turn, and then move, because you're at a slight disadvantage. You're not moving slightly more of the time. Yeah, so there's a little bit of subtleties going on here. Dynamics between the evolution of behavior and the evolution of communication.
Has anyone repeated the experiment, given the males the rule that they can't turn in the same direction more than 2 or 3 times in a row?
You could, but that's less fun, right? You want to see what evolves. Of course, we could try and give the males strong hints and give females the strong hints about what song to emit under what conditions. But we're just interested in this experiment at optimizing a particular loss function or optimizing a particular behavior, which we built into the experiment from the beginning. And these agents evolve a flexible and efficient language to make that happen.
It's interesting to see at a time step 16,000, there's a large population of males that have evolved the ability to go straight when the female's typically saying to go straight, but also turn left or right, but then they die off by the end.
You're talking about, what is it, 12, 13? This
Yeah,
group,
12,
right?
yeah.
Yeah, 12, 13, exactly. So these males are capable of turning left or right. So the receiver possibly is pretty flexible. It's able to deal with a lot of different situations, but maybe the senders, the females, weren't as efficient relative to the receivers. They weren't quite sure, quote unquote, when to emit what song that would really make the efficient behavior of these males shine relative to these ones, right? Remember, we're only explicitly looking at the receivers here and not what the senders are doing. Okay. Question?
Comment.
Yep.
See, those interesting. See that they also, most of them converge relatively quick to song 1 and go forward. It's then working out the kinks with that there.
So the language itself solidifies pretty quickly. This song means this song means that. And there's twists on it, but yes, it sets in pretty early. Okay. All right. That concludes our discussion about the evolution of communication and our discussion about collective robotics in general. Obviously, collective robotics is a vast field in and of itself, and we've just looked at 2 representative examples. The point of these 2 lectures taken together is coordinated action on a large scale is super useful. Clearly, our species has done pretty well, at least so far, because we can coordinate action at a large scale, but it's also very difficult and problematic. Again, something that our species has intimate experience with. Tricky. So as we move forward into the AI and robotics era and we deploy ever more numbers of AI instances and robots and autonomous vehicles and all the rest, how do we coordinate their actions? Question 1. Question 2, how do we turn over the keys, no pun intended, and let them figure out how to coordinate and possibly communicate in order to coordinate better? Arguably, we could have had these 2 lectures back in the open-ended questions part of this course. People still don't know. We definitely know that agents can evolve coordination, and they can evolve communication in order to coordinate. It's definitely possible. How do we port that to the real world? Remains to be seen. Okay, we have 10 minutes left, so we're just going to start in on our final theme of the course, which is really what evolutionary robotics is all about. If you have your robot already and you just want to train it to do something, machine learning is for you. If you have a task that you want one or many autonomous machines to carry out, and you're not quite sure what the physical construction of that machine should be, I realize I'm biased, but evolutionary robotics is for you. We can, using an evolutionary algorithm, automatically design brain and body together. It's tricky for almost the same reason as the evolution of communication. Imagine in an evolving population, you have an evolving population of robots, and a mutation makes a slight change to the body, but not the brain. Or alternatively, another machine in the population suffers a mutation that changes the brain, but not the body. Why is that situation and evolving bodies and brains so much more difficult than just training brains of fixed-bodied machines?
As the brain's evolving, it's probably evolving with the body and how that body functions in mind. When you change the body, that's going to alter how the brain affects the body in unexpected ways.
Absolutely. So body and brain communicate with one another. Depending on which way you look at it, one is the sender and one is the receiver, right? And they get used to each other. They know that if the body is like this, the brain should be like this and handle situations like this. If the brain is like this, the body can adapt to the brain, and over evolutionary time, they start to match up. But maybe that whole population of robots is sitting on a local optima, and there's a different pair of bodies and brains that would be even better at whatever us humans want those machines to do. But now we got a chicken and the egg problem. If a mutation even changes a body so that it's a little closer to this hypothetical platonic body that's really good, it breaks the connection with the brain. How do we simultaneously improve these 2 things?
I don't have a great understanding of it, but like how sometimes when someone has a transplant, sometimes that transplant can be rejected because that's a slight change and it doesn't quite understand how those are working.
Yeah, good point. So is an organ transplant an example of this? Kind of. It's usually the immune system that has a problem with it. It's actually non-self discrimination. Your immune system is really good at self, non-self, and it says, that's not self, reject. So it is in a way dealing with a mismatch between self and something else. Okay. All right. So I think we got 5 minutes left. I'm just going to sort of talk you through these these 5 lectures at a high level, and we'll dive into lecture 20 next time. This idea of evolving bodies and brains has been around for a long time. So we're going to go back. We're going to go back in lecture 20 to the beginning of the field, the early 90s. We're going to see an experiment in which someone built their own physics engine and then evolved robot bodies and brains in that simulation. It works, but only up to a point. So the robots we're going to see in this lecture are made up of only a few parts, 6, 8, 10 parts, like what you've been building in your assignment. So there was a demonstration back in the early 90s that this works, but it didn't work very well. It doesn't scale very well. We're going to then we're going to jump forward in time to about 8 years ago, and we're going to look at evolving the bodies and brains of soft robots. And it turns out that when you evolve bodies and brains of soft robots, it's actually a little bit easier. Why? Given what we've just discussed over the last few minutes.
Soft robot, the physiology of the body is less restricted.
It's less restricted. It's soft. It's literally pliable, and it can twist and turn and stretch to adapt to what the controller is pushing and pulling on the soft material of the body to do. So we're going to look at evolving bodies and brains of rigid robots, which is where everything started, evolution of soft robots. Then we're going to talk about, in lecture 2022, differentiable robots, which some of you have already started to tinker with if you've done the differentiable assignments. How do we take how poorly the robot is doing at whatever we want it to do, trace that poor behavior back into the body and brain, identify which parts of the body and brain are causing the robot to do a poor job at whatever you want them to do, and non-randomly tune body and brain so that, first of all, you don't break the other half of the system. Body doesn't break brain, and brain doesn't break body. And that slight change to body and brain produces a new robot that does a slightly better job at whatever you want it to do. That's differentiable robots. We're going to then look in lecture 23 at evolving bodies and brains for what are now known as meta-robots, robots within robots. You are a robot made up of robots, made up of robots, made up of robots. You are made up of organs, which are made up of cells, which are made up of macromolecules, all of which have their own sense, think, act cycles. When we get down to macromolecules, the think is kind of in quotation marks, but there you go. And then we'll end again with evolving literal bodies of biological robots. And as was reported in the literature 3 weeks ago, we can now evolve the brains of biological robots as well. We'll get there right at the end. Okay, we'll dive into more details next Tuesday. Remember, you have a milestone due next Tuesday. Have a good rest of your week.